Okay, so let's take a look at a logistic problem. It says a state game commission releases 40 elk into a game refuge or a park. After 5 years, the elk population is 104, and this represents the differential equation of this elk. How many elk can the environment support in the long run? So first thing I do is I always check that the differential equation is written in the form that we recognize. So this is the form that we want, that we have from up here. So notice it is written in that form. They're just using P instead of Y. Notice that limiting capacity, or that L, is 4,000. So remember, this is, in the long run, what happens. So this is at 4,000. So in the long run, because of space, resources, water, food, etc., the park can only sustain 4,000 elk. That's all we need to be able to pick up. Now, so this is really a horizontal asymptote on the graph, that 4,000. It doesn't mean that the graph can't go above or below, right? We can cross over horizontal asymptotes, but if it goes a little bit above, that means that there's not enough resources, so it's always going to go to 4,000. So it's just in the long run, what are we approaching? Now, let's look at a different type of question. This is talking about population rabbits, and this is our differential equation. Again, I always just double check that's in the form of our general model. So ky 1 minus y over L, and it looks like it is. Your L in this problem happens to be 10. And it says we're going to measure it in hundreds of rabbits. There were 100 rabbits to start, so y of 0 equals 1. So really, the 1 represents 100. It says, what's the fastest growth rate in rabbits per month that this population exhibits? So we learned before that the fastest growth rate, the steepest slope, which is what this is asking, always occurs at 1/2 of that limiting capacity. That L in this problem is 10, so when there is 500 rabbits, right, this is in hundreds, so when there are 500 rabbits, you're going to have the steepest slope. But this is not asking how many rabbits there are. This is asking what is that growth rate. So it actually wants you to come up with that rate, which is the slope. So we are going to plug in 5 in for the y. And if you do that, you're going to get 2.5, which is going to be 250. So make sure you are answering the question that it's asking, right? It's not asking for the number of rabbits when you have the fastest growth, which is 500. It's asking what is that growth rate, and it's the derivative, okay? Now, we're going to do the same problem using Euler's method. So remember, Euler's method is where you do an approximation using like a table idea. So we're going to start with the initial value that they gave us. So at time 0, we have 100 rabbits, or 0, 1. We're going to go up to a step size of 1. So your x's are always going to go up by 1. And we're trying to get to 2. So first step is we need a slope. So slope is what? dy dt is y, 1 minus y over 10. I'm going to plug in 1 for y. And if I do that, this is what I get. This is 9/10, so either 9/10 or 0.9. Whichever one you want to use. So now that I have my slope, my next point, the x, goes up by 1, so it's 1. And then this is your change in your y, right? So this is dy dt, this is your y, so if I add 0.9 to 1, it becomes 1.9. So there's my next point. So let's do the same thing. dy dt equals y, 1 minus y over 10 again. Let's plug in 1.9 here. And you're going to have to do some arithmetic here, and this is going to be 1.539. So again, the idea is this is your previous y, this is dy dt, your change in y. You can just add it to here. Or if you want to write it as an equation of a tangent line like we've done in class sometimes, you can do that. So y minus 1.9 equals the slope. And then x minus delta x, that's your delta x, which is 1. And then all you're doing is doing this. And this ends up being 3.44. Answer, it's 100, so it's 344. Now, last one is now the same problem, but can you identify the slope field that matches with this? Okay, I know this is a little bit blurry, so it's hard to tell. But we did notice here that our carrying capacity was 10, so we want to see a horizontal asymptote at 10. So I know it's a little bit hard to see, but it looks like here you're approaching 10. This one, there's definitely not a horizontal asymptote at 10. This one, no, because it's still growing. And this one does not look like it is growing either. This one, it looks like it's going up and then it's flattening out. This one, it's kind of coming down. It's not even exponential growth. So this is the only one that makes sense based on our logistic.